let's move on to this worksheet for section 19.5. This is going to give us some practice using the integrated rate laws and the half-life equations. And the first problem that we're looking at, we are given a rate constant, we're given an equation, we are asked to calculate how long, we're told it's second order, and we're asked to calculate how long it would take for the concentration to drop from initial to a final amount. So in general, when you're doing these kinetics problems, anytime that they are asking you to calculate the concentration at a specific time, or some kind of calculation like that, you're always needing to use the integrated rate laws. So we are going to look up for the second order reaction, the integrated rate law. That is 1 over A at time t equals kt plus 1 over A initial. And so what do we know in this problem? We know the value of the rate constant, k. How long in seconds, that's what we're trying to figure out. That's our time. How long would it take for the concentration to decrease from 0.6, so that's our initial concentration, to, we're going to 0.28, so that's our final concentration, or the concentration at this particular time. So all that we have to do here is plug these numbers in. 1 over 0.28 is equal to 0.54 molarity to the -1 times time, the thing that we don't know, plus 1 over A initial, which is 0.62 molar. If I'm going to use some units, I need to use all units. Honestly, with kinetics problems, I probably shouldn't do this, but it's easier to just not use units a lot of times. So no judgment if you agree with that. So now we just have to solve for t. And I think what I'm going to do to solve for t, I'm going to do the 1 divided by 0.28 and subtract from that 1 divided by 0.62. And that gives me 1.959 is equal to 0.54 times t. Look, I just dropped my units like they were never even there. 0.5 divide by 0.54, and so we get a time of 3.63 seconds. So these problems are pretty straightforward if you're comfortable with some weird algebra, because a lot of times we're solving for stuff that's in the denominator or doing some natural log stuff. And as long as you know which equation to use and when it's time to use them, it really is as simple as plugging stuff in. So here's our next problem. This is, oh, and also going back up to this one, notice that the equation, it never was a factor. Like, we never even needed to know what type of reaction that we were dealing with. So this one we know is a first order reaction. It tells us what the half-life of the reaction is, so that is T1 half. And we're supposed to calculate the rate constant, K. And then there's another part to the problem too, calculate the time that it takes for 95% to decompose. So this one is a little bit different. This is going to be a first order half-life. So we need to use the first order half-life equation, which is T1 half equals 0.693 over K. So since we know the half-life, we know that the half-life is 35 seconds. This time we're just trying to solve for K. And you've got to be a little bit careful here with your algebra because, like I said, you're solving for something down in the bottom. So this is going to be 0.693 divided by 35. K is 0.0198. Look at me not caring about units. Now it's asking, calculate the time required for 95% of it to decompose. So this is a problem where it's asking you specifically about time, like how much time would it take for 95% to go away? Or how much is left after 35 seconds go by or something like that. So in those types of very time-specific problems, you need to use the integrated rate law. And what are we doing? We're doing first order. So the integrated first order rate law is going to be the natural log of A at time t equals negative kt plus the natural log of A initial. So what do we know here? We know k because we just solved for k. So we know this is 0.0198. And t, this is what we're actually trying to figure out. The problem wants us to calculate time. Now this one you might be thinking, we're stuck because we do not have an initial concentration and we do not have a concentration at time t. But what we do know is that we are looking for how much time it takes for A at time t to be only 5% or 0.05 of whatever we started with. We are looking for a 95% decrease in the concentration of A. And so we can actually use this and plug it into the equation for A at time t. This is really similar to what we were doing when we were deriving the half-life. We were saying at the half-life, our concentration is going to be 1/2 of what we started with. In this problem, we're saying, okay, at this time, whatever it is, we're only going to have 5% or 0.05 left of whatever we started with. So I want to actually move this, write it in a better spot where it's out of my way. So a concentration of A at time t is going to be 0.05 of the concentration that we started with. So now we're going to plug that in. The natural log of 0.05 A initial is equal to negative 0.0198, so I'm plugging in k, times the time t plus the natural log of A at time 0. So we're going to need to do some log math, and we're going to subtract the natural log of A at time 0 from both sides of the equation, which is going to end up putting it right here. And if you forgot about that, look back in your notes on when we derived the half-life for the first order reaction, because that's where I walked through that step more slowly. And when we do that, our term A initial ends up canceling out, which is perfect. So we end up with the natural log of 0.05, that is negative 2.996. That's equal to negative 0.0198 t. So the time is 151 seconds. And again, if this step here where I moved the natural log from the right side to the left side, if that blew your mind, go back to your notes for 19.5, the derivation of the half-life for the first order reaction, because in that derivation, I went more slowly with that particular step. So here we have one more problem we can practice with. We have a first order reaction. We're being asked what is the half-life if 75% decomposes in 60 minutes? What is the half-life? So let's say for a half-life, let's remind ourselves, for first order, what is the half-life equation? 0.693 over k. So in order to figure out the half-life, we need to know the rate constant k. Well, where can we get the rate constant? We can get the rate constant from the integrated rate law. Natural log of A at time t equals negative k t plus the natural log of A at time 0. Can we figure out k? Well, we know the time is 60 minutes. And we know at that 60 minutes, 75% of our sample has decomposed. So A at time t is 0.25 of the initial amount. 75% decomposes in 60 minutes. That means in 60 minutes, you only have 25% left of what you started with, or 0.25 of whatever you started with. So the natural log of a at time t, we're going to substitute that with the natural log of 0.25 a at time 0. And that is equal to negative 60 times the time plus the natural log of a at time 0. Now here's where I'm going to do that magical natural log math again. I'm going to subtract the natural log from both sides of the equation, which means that I'm actually going to end up putting it in the denominator right here. Logs are so fun. And then the a at time 0 is going to cancel itself out, and we will end up with the natural log of 0.25, which is negative 1.39, is equal to negative 60 times time. Time is positive 0.02. What did I do here? I'm solving for k, not t. I got my things all mixed up right there. The numbers are okay, but I've got the variable wrong. Negative k times 60 minutes. So this is negative 60k, and this is k. This makes more sense to me. 0.0231. So we've solved for the rate constant k. Now we can plug it into the half-life equation. T1/2 equals 0.693 over our rate constant, 0.0231. And our half-life is 30, what unit of time do we have? Minutes, 30 minutes.